Hello everyone and welcome to our calculus notes for section 6.1. Today we're going to be talking about the area of a region between two curves. And we want to learn how to express this as a definite integral. So what I have here are two curves, f and g, and we'll just take a look at the f curve right here. And if we want to find the area under the curve between a and b, that we can see right in here, we know we can find this area by finding the definite integral from a to b of our function f of x with respect to x. Okay, and that will give us this area right in here. Now if we look over here at our next function and we look at our g function, and we want to find the area from a to b. Now we're looking for the area right in here, and we know this area is given by the definite integral from a to b of g of x with respect to x. And so that is this area right here. Now I'll just label this area sub 2, and we'll label the other one area sub 1. And what we want to try to do now is be able to find the area between these two curves. Okay, so right in here. Well, geometrically, if we're looking for this, we'll just call it a sub 3. Hopefully you can see that a sub 3 would just be taking a sub 1 and subtracting a sub 2. Okay, so if we take all this area and then we subtract this area, we're going to be left with a sub 3 right here. So if we want to write this as an integral, a sub 3 would equal, well, a sub 1, which was the integral from a to b of f of x dx, minus a sub 2, which is the definite integral from a to b of g of x dx. Okay, so this is how we would find that area a sub 3. Now we can also think about this using our representative rectangles. Okay, and it's going to apply the same thought process that we did before when we were dealing with just finding the area under one curve. So if I were to take this and divide it up into rectangles, okay, much like what we were doing before, we know the area of a rectangle is base times height. Now in this case, what is our base? The base is going to be our delta x, just like it was before. And how would I find the height? Well, if we take a look at this and we trace this over to the y-axis, I would call this f of x sub I. And then if I trace this point over to the y-axis, I would call this g of x sub I. So basically it's the function evaluated at the point. And so if I'm looking at the height here, it's going to be the difference between f of x sub I and g of x sub I. So we have f of x sub I minus g of x sub I. So if I were to find this area by plugging in for my base and my height, I would get the height is f of x sub I minus g of x sub I times delta x. Okay, and we know then that we're going to be taking an infinite amount of rectangles here and letting my delta x go to 0. And so we know that this is the same thing as taking the definite integral. So here we have the definite integral from a to b of f of x minus g of x with respect to x. Okay. Now, we could have also seen that if we take our definite integrals here with the same limits of integration, we basically would just have to combine these into one right here. So all in all, to find the area of a region between two curves, all you have to do is take the definite integral from a to b of f of x minus g of x with respect to x. Now, this is given that f of x is greater than g of x on that entire interval. So you can see our subtraction process is only going to work if we put the taller function first. So let's give some of these a try. Okay, so we want to find the area of the region between the two curves, x squared plus 2, which is right here, negative x, which is right here, on the interval 0 to 1. So from 0 to 1. So the area we're looking for is right in here. So we'll just label these here. Here's your f of x, and here's your g of x. And if we want to find this area, all we need to do is take the definite integral from 0 to 1 of f of x, which is x squared plus 2, minus g of x, which is negative x, with respect to x. And you'll notice that I do put the functions here in parentheses. Just when you're subtracting, we have to make sure that we distribute that negative to the entire function there. And so now we can simplify this. So the area will equal the definite integral from 0 to 1 of x squared plus x plus 2 dx. And so notice all I did here was change my signs and then rewrite this. Now at this point we can solve because we know how to take a definite integral. So the definite integral of x squared plus x plus 2 is going to be x cubed over 3 plus x squared over 2 plus 2x, and we're going to evaluate that from 0 to 1. So we're going to plug in our 1 first. 1 cubed over 3 plus 1 squared over 2 plus 2 times 1. And this is going to be minus 0 cubed over 3 plus 0 squared over 2 plus 2 times 0. So we're left with 1/3 plus 1/2 plus 2 minus 0. And if we turn these all into sixths, we end up with 2/6 plus 3/6 plus 12/6 for a grand total of 17/6. Okay, so not quite 3 there for the area between the two curves. Now, you may think that we're doing something new, but in actuality, we're not. If we were to look over at this example here, x squared plus 2, and before we said find the area under the curve, right? And so we, let's just say from 0 to 1 again, and we said under the curve, and we limited it here at the x-axis. Well, it turns out the x-axis is also a curve. It's y equals 0. So when we were doing our definite integral, we would go from 0 to 1, and we would do x squared plus 2, Okay, that was our first function. And then minus our second function, which was just 0 with respect to x. Okay, so we've already been doing this, but when we were using the x-axis, our second curve or function was just 0, and so it didn't equate into our definite integral. Okay, so just a little side note there for you. I want you to try the next one on your own. Go ahead and pause the video and then come on back when you're done to check your work. Alright, welcome back everybody. So you should have blocked off this area right in here and set up your definite integral by taking the upper function minus the lower function, and then that reduces right there. And one note is that you can use your calculator to find these definite integrals. So just use FNINT or whichever method you prefer, but you should have come up with an area of 50/3. Alright, next we want to talk about the area of a region between two intersecting curves. Okay, so you'll notice in all the previous examples we were going between two regions, and that would be given to you in the problem right here. Now what we're going to do is just say find the area of the region between the two curves. So we're going to take a look at two different types of functions. Functions of x as well as functions of y. So if we're looking at finding this area right in here, okay, we can see that they intersect at 2 points. And I'm going to call this the left intersection and this is the right intersection. So when we go about finding our indefinite integral, that's the left and the right that we're talking about here. And notice it's going to correspond with the x values at that point. So it's the x value of the left intersection and the x value of the right intersection. Okay? And again, this is all because we have functions of x. Now, the next part is kind of what we were doing before. It's going to be the top function minus the bottom function. So here, this one would be considered our top function, and then this one would be considered the bottom function. Okay, so all you have to do differently from what we were doing is identify the x values of the two intersections on the left and the right, and then take your definite integral. And you'll notice here, if we were trying to draw rectangles, representative rectangles, they would also be vertical. Okay, so a lot of times it's really good to start off with what type of rectangles would I use to find this area. Now in this example over here, now I have functions of y. And this is when we want to use horizontal rectangles. So if I'm finding the difference between the two curves, notice it works okay to do vertical rectangles here, but as soon as we get over here, it's not going to work because we have the height and it doesn't actually go all the way up to this other function. So that's why our vertical rectangles won't work in this case. And really what we're dealing with here are going to be horizontal rectangles. And notice on the entire section between the two intersections, if we did all horizontal rectangles, it would work out just fine. Okay, so now that we've identified we have horizontal rectangles, you can see there's two intersections. And what we want to think about is there's a top intersection and a bottom intersection. And this is going to correspond with your definite integral and your limits of integration. But because this is a function of y, what we really are looking for here are the y values at those intersections. So we're looking for the y of the top intersection and the y of the bottom intersection. Okay, and so the y of the top would go here, and then the y coordinate of the bottom function would go here. Then when we subtract our two functions, we're actually going to subtract, we're going to take the right function and then minus the left function. Okay, so you just have to think, if we took this y-axis and we made it horizontal, okay, we would take the right minus the left. So this is your right function here, and this is your left function here. Okay, so you get the definite integral from bottom to top of right minus left functions, and now dy with respect to y. Okay, so let's go ahead and try some examples here. Okay, so it says find the area of the region between the two intersecting curves, and so we can see they intersect right here, and then the shaded area that we're looking for would be right in here. Side is this horizontal or vertical rectangles as we go through this. We have to be able to make rectangles across this entire section here. So looking at this, these are actually going to be vertical rectangles. As you can see, I could make them all the way across anywhere on that interval. And let's go ahead and identify our f of x and g of x. So here's our f of x function, and here is our g of x function. And the next thing we have to do is find the intersections. To do that, we set f of x equal to g of x, and then solve. So we're going to say 2 minus x squared equals x. And then this is just a quadratic function that we want to solve, so we're going to set it equal to 0. And I'll put this in order here. And it's probably easiest if x squared is positive, so I'll change all of the signs. And then I can solve this by factoring. So we get x plus 2 times x minus 1. And so I have two solutions for x. X equals negative 2 and x equals positive 1. Okay, and you can see those right here. So here is the x sub L, or the x on the left endpoint, and then here is the x on the right endpoint, and you can see that is where they intersect. Okay, so now we want to follow this pattern right here. So this is the integral from the left x to the right x of top minus bottom dx. So the area is going to be the integral from negative 2 to 1 of my top function, which is going to be 2 minus x squared, minus the bottom function, which is just x, and with respect to x. And so if we simplify this, we have negative 2 to 1 of, well, negative x squared minus x plus 2 with respect to x. And if we just solve this using our calculator, we're going to get 9 halves. So let's go ahead and move on and try our next example here. So here we have g of y equals 3 minus y squared. So here's your g of y. And we also have f of y is y plus 1. And here's the function y plus 1. And we want to find the area between these two regions. Okay, so we're looking for this area right in here. Okay, so the first thing we have to do is identify our intersection points, okay, which are right there. And then we have to decide, do we have horizontal or vertical rectangles? Well, these are functions of y. Okay, so notice the functions of y in there. So that means we're going to have horizontal rectangles. So it's always good to draw your representative rectangle because it just kind of puts you in the right mind frame here. So here's our horizontal rectangle. The first thing we need to do then is identify the y value of the bottom intersection and identify the y value of the top intersection. Okay? And to find these intersections, we're going to set our two functions equal, so g of y is going to equal f of y. And so that means 3 minus y squared equals y plus 1. And then we're going to go ahead and solve. So I'm going to add y squared to both sides and also subtract 3 because we need to get it equal to 0. So this gives me 0 equals y squared plus y minus 2. Then I'm going to solve this by factoring. So we have y plus 2 times y minus 1. And this gives me y equals negative 2 and y equals positive 1. So let's just identify those intersections and make sure that it's correct. So here is your y equals negative 2. And here is your y equals positive 1. And you can see that it does work right there. Okay, next we have to identify the right function and the left function. So this one's definitely the right function. And this one over here is the left function. So now, if we want to find this area, we get the area equals the definite integral from negative 2 to 1, so that's the bottom y to the top y, of the right function, which is 3 minus y squared, minus the left function, which is y plus 1, with respect to y. And then we'll just simplify this here. We'll change all of our signs. And putting it in order, I get negative y squared minus y plus 2 and dy. And from here you could use a calculator and we would get 9/2 for our area. Okay, so there's two examples, one with vertical rectangles and one with horizontal rectangles, and how to deal with each of those. Alright, so we just want to go through a couple more examples here, and in letter C we want to find the area between the two curves f of x equals 3x cubed minus x squared minus 10x, and between g of x, which is 2x minus x squared. And that's going to be this curve right here. Now, in looking at this, we actually get 3 intersection points here, and we have 2 different regions that are bounded by these curves. So one of the regions is here, and then the other region is right here. So to be able to solve this problem, we're actually going to have to find the area of these 2 regions separately. So we'll call this a sub 1 and this is a sub 2. And basically by just allowing for different limits of integration, we can find the 2 different areas. So looking at this, it looks like we're going to be getting vertical rectangles here. And we can see that these are functions of x. And so that's going to work really well. But we need to find all the x values where they intersect. So let's go ahead and let 3x cubed minus x squared minus 10x equal 2x minus x squared. And notice we're going to subtract to get it equal to 0, or add the opposite actually. So we'll have a minus 2x here, and then plus an x squared here. And that's pretty nice for us because our x squareds are going to cancel out there. So we have 3x cubed, no x squared, and then minus 12x equals 0. Now we can take out our greatest common factor of 3x, and we're left with x squared minus 4, which is a difference of squares. So this is 3x times x plus 2 times x minus 2, and that equals 0, leaving us with the 3 solutions, x equals 0, negative 2, and 2. Okay, so looking over here, we know that this x equals 2, this one is 0, and then down here, this is happening here at negative 2. So to find a sub 1, it's going to equal the definite integral from -2 to 0 of the top function minus the bottom function. So for a sub 1, our top function is going to be f of x, and the bottom function will be g of x. So here we're going to get f of x, 3x cubed minus x squared minus 10x, and this is going to be minus g of x, which is 2x minus x squared. This is with respect to x, and if we simplify that, we are going to get 3x cubed minus 12x dx, and when we evaluate this, we get an area of 12 here. So a sub 1 equals 12. And then let's go ahead and find a sub 2. Okay, so in this case, we're going to go from 0 to 2. And now, what is our top function? Well, our top function is going to be g of x. So now we get 2x minus x squared minus 3x cubed minus x squared minus 10x. Remember our parentheses there. And that'll be with respect to x. And then we can change all of our signs and simplify this. And we get a sub 2 is the definite integral from 0 to 2 of 12x minus 3x cubed dx. And when we evaluate this, we also get 12. So all in all, to get our total area, it's a sub 1 plus a sub 2, which is just 12 plus 12, or 24. Okay, so just be aware that when you're finding the area between two curves, that you do have to take into account all of the different intersection points, and you may have to find two different areas separately. All right, let's take a look at one with some trig here. So just in the interval that's shown, we want to find the area between sine x and cosine x. So we're looking for this area right in here. And you can see that we have two intersection points. And we also have vertical rectangles, or functions of x, and so we do need the corresponding x values here. And so what we need to do is let sine x equal cosine x. And one way you can think about solving this is we can divide both sides by cosine x. Kind of a little trick there. And what happens then is sine x over cosine x becomes tangent x. And we want to know where this equals 1. Okay? And on the interval shown, tangent x equals 1 at pi over 4 and 5 pi over 4. Okay, so then we have our definite integral from pi over 4 to 5 pi over 4 of the top function. Well, the upper function here, this is going to be sine x, and then the bottom function is going to be cosine x. So we have sine x minus cosine x dx. And then we can just use our calculator here, and we're going to get an approximation of about 2.828. All right, let's move on. In our next example, we actually have three functions here. Y equals x plus 6, y equals x cubed, and y equals negative 1/2 x. Okay, so we'll just identify all of these here. Here is y equals x plus 6. The curved one, this is y equals x cubed. And then this one is y equals negative 1/2 x. And then our area is going to be right in here. Now in this one, if you look, we have a couple intersection points. We have one over here, we have one right here, and one right here. And so this again is going to get split right here in the middle intersection point, and we're going to actually get two separate areas that we're going to have to find. So we do need to find our intersection points. So for this first intersection point right here, that is where x plus 6 equals negative 1/2 x. And if we solve this, let's see, I can subtract x to both sides. We get negative 3/2 x. And if we multiply by negative 2/3, that'll take care of that. Okay, and that leaves me with negative 4 equals x. And it looks about right. So we have negative 4 there. And let's take a look at our second intersection right here. So this is going to be where negative 1/2 x equals x cubed. So we'll just add this to the other side and say 0 equals x cubed plus 1/2 x. And we'll factor out an x. Okay, so this one right here gives me x equals 0, and this one has no real roots, so we don't have to worry about that one. And x equals 0, we could probably see that that was the case right there. And then for our third one, let's find where these two intersect. And that's going to be where x cubed equals x plus 6. And so we'll subtract there. And here we may just want to think about it and estimate. It looks like it's about at 2. If we plug 2 in this, does it work? 2 cubed minus 2 is 8 minus 2, which does equal 6. So this happens at x equals 2. Okay, so we do have our 3 x values right here. So if we want to find a sub 1, it's going to be the integral from negative 4 to 0 of the top function, which is x plus 6, minus the bottom function, which is negative 1/2 x, with respect to x. And if we simplify, negative 4 to 0 of, let's see, 3/2 x plus 6 dx. And when we calculate this, we get 12. And then a sub 2 is going to be the integral from 0 to 2 of the top function, which is still x plus 6, minus the bottom function, which is x cubed, with respect to x. And if we just put that in order, we'd have x plus 6 minus x cubed, really nothing changing there. And when we calculate this, we get 10. And so overall, the total area will be 12 plus 10, or 22. All right, so this page is just showing some different ways that you might see the area between two curves. All right, so that is section 6.1 on finding the area between two curves using definite integrals.